In this video, we're going to explain how to calculate the inverse of an integer mod p. So basically, what that means is we're given an integer a, and the question that we want to answer, the thing we want to do is find an integer b such that a times b is congruent to 1 mod p. So what that means is that if you calculate ab, when you subtract 1, it's a multiple of p. Okay, that's what we're trying to do. And in the video on the extended Euclidean algorithm, I basically explained how to do it. So how do we do this? So by the extended Euclidean algorithm, so a and b are relatively prime, right? Because we have, so I guess I should have said that. So an integer a with GCD a and p equals 1. So when you have that, we can do this. So by the extended Euclidean algorithm, we can find integers m and n such that a times m plus b times n equals 1. Or a times m plus p times n equals 1. Okay. So, and now when we reduce this equation mod p, so we take the remainder when you divide by p, we get, well, p times n mod p is just going to be 0. So you're just going to get a times m mod p is congruent to 1 mod p. So that's our multiplicative inverse, m. So that m is our b in the problem. Find an integer b such that ab is congruent to 1 mod p. The integer b that we're looking for is m. Okay. So just a reminder that when we talk about the multiplicative inverse of a mod p, okay, so this means the mod p multiplicative inverse. So in the real number system, the multiplicative inverse is just the reciprocal. So the multiplicative inverse of 2 is a half, because 2 times a half is 1. That's not what we mean when we talk about the multiplicative inverse in mod p arithmetic. This is like a different number system, right? It's a different number system. The multiplication in mod p is related to the multiplication of real numbers, but it's a different thing. And when we talk about inverses, we mean with respect to the mod p multiplication. So we get 1 when we do the mod p multiplication. Okay, that's why when we're talking about the multiplicative inverse of a in mod p arithmetic, we mean not that a times m is 1, it's that a times m is congruent to 1 mod p. Okay, so now let's look at an example. But I just wanted to emphasize that because I've noticed that that's something that is confusing to people who are learning this. So the example we're going to do is find the multiplicative inverse of 10 mod 37. So we're looking for an integer between 1 and 37 such that when you multiply it by 10, it leaves a remainder of 1 when you divide by 37. Okay, So the way to do this is to look at the extended Euclidean algorithm. So first we have to do the Euclidean algorithm, those equations. So the first equation we get is 37 is 3 times 10 plus 7, right? So now we have 10 and 7. So the second equation is 10 is 7 times 1. I'll be consistent and do 1 times 7 plus 3. And the third equation, so we have 7 and 3. 7 is 2 times 3 plus 1. And so the GCD is the GCD of 3 and 1, which is 1. So we have a 1, and with that we can stop. So from the first equation, so now we're doing the part where we express the GCD, which is 1, as 10m plus 37n for integers m and n. Okay, well, the first equation tells us, so I explained how this works in the video on the extended Euclidean algorithm. So we write 7 is 37 minus 3 times 10. And then the second equation tells us that 10 minus 7 is 3. And now we substitute my equation for 7 in terms of 37 and 10 in. So it's 10 minus parentheses 37 minus 3 times 10 is 3. And when we combine terms, we get negative 37 plus 4 times 10 is 3. And then now we bring in the third equation. So 7 is 2 times 3 plus 1. So 1 is equal to 7 minus 2 times 3. And 7 was 37 minus 3 times 10. And 3 was negative 37 plus 4 times 10. So now when we combine terms, we get 3 times 37. And then, let's see, when you distribute the negative 2, you get negative 8, and then you have a minus 3, so it's minus 11 times 10. Okay, so 1 is 3 times 37 minus 11 times 10. You can check that that's correct. And now we reduce mod p, which is 37, to get 1 is congruent to negative 11 times 10 mod 37. But usually when we work mod 37, we want to work with numbers from 0 to 36. So, and negative 11 mod 37 is 26, right? Because negative 11 plus 37 is 26. So 1 is congruent to 26 times 10 mod 37. And so the multiplicative inverse is 26. So 26 is the inverse of 10 mod 37. You can check that 260, 26 times 10 minus 1, so that's 259, is, so let's check. So 26 times 10 is 260. 260 minus 1 is 259. Is that a multiple of 37? It turns out yes, because you get 7. So that's how you find the multiplicative inverse of an integer mod p. Now if you're working mod n, where n is not a prime number, then not all numbers have multiplicative inverses. So for instance, if you're working mod 6, then 2 and 3 don't have multiplicative inverses. 4 doesn't have an inverse. And that has to do with the fact that they have a common factor. So you can't multiply 4 by some number, some integer, and then subtract 1 and then get a multiple of 6. But 5 does have an inverse mod 6. So you can do 5 times 5. 5 times 5 is 25. That's congruent to 1 mod 6, because 25 minus 1 is 24, and that's divisible by 6. And in general, when you're looking mod n, the only numbers that will have multiplicative inverses are the ones that are relatively prime to n. So has no common factors with n. In the case when your n is a prime, then that's all the numbers. So besides 0. So every non-zero number in mod p arithmetic has a multiplicative inverse. And this algorithm, the extended Euclidean algorithm, shows you how to actually find what the multiplicative inverse is. And this is something that is important to do, for instance, in solving congruences, but in cryptography, it's one of the steps in something called RSA, the RSA crypto system. And one of the things that I think many people find confusing in the different steps is there's this one step where you're supposed to find the multiplicative inverse, mod p, or mod, something that's like relatively prime to the thing that you're trying to invert. And then one common question is, well, how do you actually do that? And the way you do that is to use this extended Euclidean algorithm. Okay, that's it for this video.